Now, let's begin the lecture. The title is Sustainable Computing for a Data-Driven Society. There are various definitions of a data-driven society. The term cyber-physical system was coined over 20 years ago in the US. Cyber refers to the digital world, physical to the material world, with the interaction occurring between them. In Japan, too, innovation efforts in 2021 gave rise to the concept of Society 5.0. On the right is a rough schematic of Society 5.0. This is also a cyber-physical system involving large volumes of data flowing from the physical world to the digital world, sometimes with real-time control. In that sense, you can think of Society 5.0 as a cyber-physical system defined by large volumes of data and real-time control. The goal is advanced interaction between people and things in the physical world. So the purpose is not necessarily to interact with the cyber itself, but for people to have advanced interactions with other people or things. When you want to go somewhere, you probably look at a map on your smartphone, and you end up walking while looking at your smartphone the whole time. When I was your age, we didn't have anything like that. So we'd buy a proper map and look at the utility poles on the side of the road, checking what the current address was, and get around that way. In other words, we were interacting with the physical world through this book. Using the cyber smartphone makes this interaction much easier. In that sense, it enables advanced interaction. What's happened in terms of technological advancement is that measurement and information processing technologies have advanced significantly when bringing information from the physical world. For example, in the past, there was the Human Genome Project. They said it would take over a decade to sequence the human genome. But nowadays, genome sequencing can be done for around $100 to a few $100s, making it possible to diagnose diseases. There have also been various structural changes in the physical world. Lots of things have gone online since COVID, about 6 years ago, such as this very lecture. I don't know how we could have managed this lecture without that, but we're able to do it now. And one more thing, and this is one of today's topics, the power supply issue. Just as a bit of background, this isn't exactly general knowledge. I'd like to talk about power. This is an excerpt from some documents by the Federation of Electric Power Companies of Japan and the International Energy Agency, IEA. Put simply, the world uses 28 times 10 to the 15th watt-hours of energy. Japan has about 1 times 10 to the 15th watt-hours, which means we use just over 3% of the world's total. Trillion kilowatt-hours is the Japanese way of expressing it, but since trillion and kilo don't mix well, I'll stick to powers of 10 from here on. This means Japan's total energy use is roughly 1 times 10 to the 15th. And one more thing, with all the recent talk about carbon-free energy, I'll touch on that as well. This is the IEA's 2024 Energy Outlook. 2024, meaning there's data up to 2023. It goes like this. With the green, clean energy rising gradually, and it will likely keep going up in the future. In contrast, fossil fuels are expected to decline. But even so, from 2023 to the present, fossil fuels account for 80%. The projection for 2050 is shown on the right in the bar graph. If you try to do it using only CFE, you get the bar on the very right. The currently announced policy scenario is the one on the very left. Looking at that, it seems like fossil fuels will still account for 58%, meaning we're still far from achieving our goals. Data center energy consumption. I'll be discussing AI today as well, and this will come up again later. But this is from an IEA report on energy demand from AI, or how much energy is required for AI operation. This is a report that came out last year. So the figures up to fiscal year 2024 are actual data, and beyond that are projections. The different colors show the different types. If you look at the very top, you can see that it's roughly 415 terawatt-hours in 2024, or 1.5% of global energy consumption. In 2030, it'll be 945, or roughly 1,000 terawatt-hours. This is equivalent to Japan's entire consumption. The global energy demand from AI will be the same as Japan's entire energy consumption. In other words, the equivalent of one Japan. This was released last year. And when it came out in April, Nikkei published an article aimed at data centers, saying energy demand would double, and how it was quite the concern. Today's lecture is under GX Inspire, so I'll be going into some of the finer details. But as you can see, there are many different types of computer systems, from supercomputers and smartphones to very low-power devices scattered throughout real-world environments. The reason there are so many is, of course, because there is a trade-off involved. The higher you go, the more performance matters over power, while the lower you go, the less performance is required, and so low power becomes more important. Toward the bottom are devices that have to function with batteries for years, so there's that trade-off. My specialty is computing, and when building computers and systems, we optimize and design them according to this trade-off. The supercomputer at the very top. I have some background experience on, so I'll touch on that first. There's a performance ranking of supercomputers called the Top 500. It's updated twice a year and ranks supercomputer performance from 1st to 500th. The most recent one is from November of last year. As for how performance is measured, they cannot be evaluated fairly unless they run the same program. One well-known program, called LINPACK, involves solving systems of linear equations, or in other words, scientific computing. Of course, being able to solve systems of linear equations doesn't mean it can do everything, but it is a useful metric. If this runs fast, you know certain programs will run fast, while others won't be affected. That's why it's used as a standard benchmark. I've listed the rankings from 1st to 7th here. Currently in 7th place is Fugaku, which you all know about. The ones listed outside the rankings, in 42nd and 81st place, are the two in operation at the Information Technology Center. I wrote these in because I'm biased, of course. 42nd and 81st are in operation right now at the Information Technology Center in Kashiwa. There are a lot of different terms like effective performance, peak performance, and power efficiency, which I'll explain next, but peak performance is the performance achievable under ideal conditions. For example, when considering the top performance of a car, this would be performance under highly ideal conditions, such as no air resistance and a perfectly straight road. This is determined when the system is built. Effective performance is the processing performance achieved when executing a program. In this case, the performance you'd get when solving these systems of linear equations. But this is the peak, so this gives you a rough idea of what percentage performance you can expect to get. I think many of them are around 70% these days. What I just mentioned is execution efficiency. Calculate this, and it shows how much of the system's capability is actually being used. Performance is measured in flops, as it says here, which indicates how many calculations can be performed per second. P stands for peta, which means 10 to the 15th. As for what the trajectory has been, the horizontal axis is the year, and the vertical the performance. This is effective performance. Each tick here is a 10-fold increase, so a logarithmic scale where each step is 10x. So then, this jagged line with the orange or brown triangles represents the performance of the top-ranked supercomputer for each year. Supercomputers, when they come in first, tend to stay that way, so some are the same, and then the year after, a different one comes out and becomes first, and so on. The fact that this can generally be drawn as a straight line, sloping up to the right, means performance has been improving exponentially. But to build a first-place supercomputer, you need a lot of technology and money. And so all of these came about in the form of national projects. Recently, it's been national research centers, like the National Institute in the US and the Riken in Japan, that develop and operate these #1 supercomputers. The 500th ranking is also actually important. The green here represents the sum from 1st to 500th place. The 500 rankings won't all be filled with national projects, which means social demand accounts for the total sum from 1st to 500th place. The line in the image is this metric, and that is also rising exponentially. This is a general reflection that demand for computing power or computational capability is increasing exponentially. And then there's power efficiency. I didn't explain it in the previous table, but it's on the very right, power efficiency. In terms of cars, efficiency would be how many kilometers it can travel per liter. This is power efficiency, and it's quite important. This is as of November 2024. But each system, from 1st to 500th place, has been plotted in this chart. The vertical axis is power efficiency, performance per unit of power consumption. Naturally, the more to the left a system is, the faster it is. The faster systems tend to have better power efficiency, meaning they deliver higher performance per unit of power. Move to the right, and there are older systems with somewhat lower power efficiency. And newer systems, of course, are more power efficient. Fugaku right now is around here, and you might think that means it has poor power efficiency. But this means when it was first launched, it actually had the highest power efficiency. In that sense, improving power efficiency is essential for improving performance. When I say power efficiency improved tenfold over 10 years, this figure on the right, which I've just changed, is the state 10 years ago. This is where we are now, and this is 10 years ago. The charts are similar, but they differ by an order of magnitude. In other words, power efficiency has increased tenfold over 10 years. Written down here are the top systems in recent years, and as you can see here as well, power efficiency has been improving over time. Building a top machine is a national project, so while funding isn't unlimited, people can spend the money and use the electricity that's needed for it. But technically speaking, you have to improve power efficiency if you want to improve performance. Specifically, power consumption is proportional to the amount of heat generated, and it must be kept below what can be dissipated through cooling. Otherwise, the system overheats and can fail, so the amount of heat generated must stay within cooling capacity, and the amount of heat that can be removed is essentially determined by the size of the facility. Whether you cool with air or water, ultimately, how much heat can be removed depends on the physical space available. If you want to install a supercomputer in a moderately sized building, the cooling capacity is fixed, and if you want to improve performance, within that constraint, you have to improve power efficiency. From here, I'd like to talk about low power system design. It'll get a bit more technical, and you might get a little sleepy for about 5 minutes, but I'll briefly explain how computers work. If you're from a science background, this may be something you've already learned. At a basic level, it's all electrical switching. High and low voltages are transmitted through switching, and we treat those high and low levels as 0 and 1 to perform binary computations. What's commonly used today is a structure called CMOS. It consists of 3 terminals: gate, source, and drain. The gate acts as a switch, and depending on its voltage, high or low, the N-type and P-type behave differently, either conducting or turning off. In other words, simple switching is controlled by the voltage applied to the gate, and these, NMOS and PMOS, operate complementarily as a whole. So why does it consume power? Take a NOT gate as an example. The left is input, the right is output, and the output is the inverse of the input. For example, if the input goes from 1 to 0, from high to low, when it becomes low, the PMOS conducts and the NMOS turns off. Only the upper path is off, and since there is a load capacitance at the output, current flows, charging it up, so the output becomes 1. So with this kind of switching, when the input is 0, the stored charge causes the output to become 1. In other words, it inverts. Because current flows, heat is generated, and this is where power is consumed. Now in the opposite case, we just did low, but when we switch to 1, there is charge that has already been built up. When switching is conducted like this, it's the upper path now that turns off, the lower path conducts, and the charge is discharged. The charge in the load capacitance disappears, and the output becomes 0. This kind of frantic switching is how computers work, on a basic level. As for why this consumes power, I think you can see that it's due to the charging and discharging. When heat is generated here, it's due to that charge and discharge. This goes back to high school physics. But the energy is 1/2 CV squared per operation. The amount of energy, or power, depends on how many times per second this happens. In other words, the clock frequency. Since the input doesn't always change, we account for that with switching ratio. So it's proportional to CV squared, F and A. Recently, there's also something called leakage power consumption. Even though it's supposed to be switching, even though it's supposed to be off, as devices scale down and a significant amount of current can leak, causing the issue of leakage current. This is how power consumption works in these CMOS circuits, or in the basic components of computing. So when thinking about low power design, you end up wanting to change the voltage. The relationship between transistor switching speed and voltage. What determines this switching speed? The speed of the computer, the switching of the transistors, is the time it takes for the output to respond to a change in the input. This is the same as before, but when it becomes low, current flows and starts charging up. So how long does it take for the output to change after the input changes? It's the time required for this load capacitance to be charged up, for the charge to accumulate. If the current is high, it charges up right away, since current is, of course, proportional to voltage. Well, basically, I did write approximately. It isn't strictly proportional, but it is roughly proportional to the supply voltage. Therefore, the higher the supply voltage, the faster the switching becomes. This is the diagram from earlier, CV squared FA. So increasing voltage makes it faster. But for low power design, we actually want to lower the voltage. And since this specific factor acts as a square, if we want to reduce power for the sake of low power design, we want to lower V. However, as you can see from this earlier diagram, if you lower the voltage, the logic is that switching slows down and performance drops proportionally. Something that has been used for decades now to address this is what's called a chip multiprocessor, or a chip with multiple processor cores. This is a photo of a chip from about 14 years ago, which has 6 cores. Multiple processor cores means each core operates at a low voltage and low speed. But with multiple cores, you can increase performance through parallel processing. I've laid out this simple calculation as an example. In the case of 2 cores, let's say the voltage of each core is 2/3. Consequently, the performance also becomes roughly 2/3. But since power is a square, it becomes 4/9. If you line up 2 of these cores, the performance is 2/3 times 2, so 4/3, while power is 8/9. This means performance goes up while power consumption actually goes down. So ultimately what they say is that it's better to have 2 people working slowly than to have 1 person working hard on their own. That's why these multiprocessors and parallel processing are being used in various places today. I thought if I only showed you material from around 15 years ago, you'd think I was just reusing old stuff, so I've brought new material as well. I think this was announced around February of this year. But it has all these cores. If you look to the right, you can see it's packed with them. But what I want you to pay attention to here is that they're promoting these things called base frequency and maximum frequency. Base frequency is essentially the frequency the chip usually operates at under normal conditions. However, there's this turbo feature for when higher performance is required. By increasing the voltage, the frequency can be pushed up to this higher level. When you raise the frequency, performance increases accordingly. But power consumption also increases significantly as a result. This is also defined as TDP, or thermal design power. This is a set limit where consuming more than this amount is considered problematic. In practice, this means that if the chip is operating at maximum frequency, this of course means heat is generated and the temperature rises. The system detects that and lowers the frequency. And on the right is the recommended customer price. Basically, it's just a matter of the faster it is, the more expensive it is. That's what's being shown here. The chip in the diagram from earlier only had 6 cores, but nowadays, technologically speaking, we're capable of mounting around 80 cores. The question is how to deliver performance while also limiting power consumption. And there are various products being released that try to do that. Right now, we're talking at the level of transistors. The relationship between performance and power, this CV squared FA formula. There's also leakage, so you get a curve like this. So let's say that if you only need this much speed from a transistor, setting the voltage here will allow it to perform at its best. But the system as a whole is not that simple. Currently, a single chip contains billions of transistors. So what do we do in that case? Performance is determined by the performance of the bottleneck. Power consumption is determined by the total sum of the whole, so you can run the inactive component slowly or disconnect power to unused components. For example, if you run the inactive components at a slow pace, performance doesn't change when the inactive people are working slowly. But because power consumption is reduced in these slow-moving areas, we're able to reduce power consumption while maintaining performance. Therefore, figuring out how to find these inactive bottleneck components and run them slowly is very important. From this point on, the topic isn't quite as technical, so I'd like everyone to wake up and pay attention. You might be asking, there are parts that aren't busy? This is a bit of a digression, but here's a simple quiz. Suppose there are 100 cards with numbers or various tasks written on them, and you're told to add them all up. Which one would be faster? A mental calculation expert or a marathon runner with a calculator? Naturally, since speed of calculation is what matters, you'd think it's the mental calculation expert, but you must be thinking, since I'm bringing it up here, that there must be some kind of catch. The answer is, if the cards are on the desk, the mental calculation expert is faster, but if the cards are scattered across a marathon course, then it's not about the calculation itself, it's about how you go and look at the cards. In that case, the marathon runner would end up being faster. You might think this is just a quiz, but this is the case for actual computers as well. When the actual calculation part is the heavy process, we call it compute intensive. That's relatively close to the first case. Meanwhile, there are also cases where just bringing in the data is the hard part, which we call memory intensive. Some processes fall into this category. Since the bottleneck changes depending on the situation, we need to apply those low-power technologies I mentioned earlier. Since I'm a bit short on time, I might have to skip ahead. But I think everyone here knows about the supercomputer Fugaku. It features something called an eco mode. Eco mode basically cuts the calculation capability roughly in half. So when would you use this? If a task is memory intensive, the calculation itself isn't the heavy part. In those times, you can reduce power consumption without changing performance. Because I'm a bit short on time, I'll jump to the conclusion. For compute-intensive tasks, power consumption is reduced, but naturally performance is reduced as well. For memory-intensive tasks, performance remains unchanged, while power consumption is significantly reduced. I've touched on this briefly, just to show that these principles apply even to supercomputers. So that was supercomputers. But now I'll touch briefly on IoT devices, where low-power design is most critical. The breakdown of power consumption in a sensor node naturally depends on application, but generally, there are long standby periods where the CPU isn't being used. Monitoring here refers to environmental monitoring. HEMS is what is written at the bottom, Home Energy Management System, and on the right is heart rate monitoring. These are in pie charts, which is a bit confusing because the circles are the same size. But naturally, the one on the left uses significantly less energy overall. This is the breakdown. The radio component versus the CPU consumption component. However, the key is that these are divided into active and idle states. It depends on the device, but the CPU being idle basically means the CPU's on standby, not doing anything. And yet it's still accounting for this percentage of power consumption. Depending on the application, this means quite a lot of wasteful power consumption. But for something like heart rate monitoring, the sensor has to be running constantly, so it's quite hard to shut down the CPU. But then that results in all of this. I can't go into too much detail on that today, but that's how it's determined. By cutting off the power at a very fine-grained level, we can reduce the power consumption during CPU idle states. But if you just cut the power, the system forgets what it was doing. So we have to use non-volatile memory. Most of you are familiar with non-volatile memory in the form of hard drives or flash. But these are a bit slow, and faster ones made of various new materials have come out. Using these while cutting power at a fine-grained level and using memory that doesn't forget what it was doing, we can get normally off computing, where the device acts as if the power is off, even while in operation. This is particularly effective for IoT devices that collect data in the real world, which has made it a very important technology. Now that we've covered supercomputers and IoT devices, I'd like to move to the middle ground, data centers. This is the same chart from earlier, which shows that, by 2030, data center consumption will be equivalent to the energy use of all of Japan. One comparison cited here is that a single Google search request uses 0.3 watt-hours, but doing the same on OpenAI's ChatGPT uses about 3 watt-hours, which is a tenfold increase. It depends on what you ask, of course, but it's roughly 10 times more. In the past, we might have relied on simple searches, but that's no longer the case. And so it's been widely reported that this much energy is consumed with every request. Another thing is that AI is being used more and more, particularly in data centers, and this chart shows the computational requirements for AI. This chart's a little busy, but the horizontal axis is the year, and the vertical axis is what we call the training compute. Think of this as the amount of calculation needed for AI training. Essentially, the processing volume. Note that each tick on the scale is 100, not 10 but 100. You can see it's rising like this, growing exponentially, since around 2010 when deep learning emerged. The slope has steepened significantly. Especially recently, there are many language models, notably LLMs. A lot of these language models are being released, and we all, myself included, rely on them quite heavily now. But I think it's vital to first understand that the amount of calculation required, the computation needed for training, has increased tremendously. As for how much energy AI is actually consuming, I've brought in a few visuals from that IEA report from earlier. This is what the IEA calls a global map of data centers. Whether every single country is covered is a bit debatable, but the size of each circle represents the power consumption. From this map, you can get a general sense of which regions are using AI. The US uses AI the most, followed by countries like Japan and those in Asia and Europe. This is the 2024 global map released by the IEA. There was something in this IEA report under Energy and AI that I was a bit impressed by. It's about the manufacturing cost involved when creating a chip. In thinking about making computing more energy efficient, I often talk about the need to reduce power consumption, not just during operation, but during the manufacturing stage as well. This report by the IEA, the International Energy Agency, makes the point that the energy used during manufacturing is equally important. On the left here, it shows how, as technology advances, or as you move further to the right, or further along in terms of miniaturization, the manufacturing energy per wafer increases significantly. And the chart on the right shows which is larger, the energy used during manufacturing or the energy used during operation. This chart says that manufacturing energy accounts for 20%, but I think it isn't the number 20 itself that's important here, it's the assumptions behind it. With operation, you first need to consider servers. The assumption is a 5-year lifespan. The server will only run for 5 years. What's more, they assume the server is running 24/7 at full capacity for those years. Naturally, if a device has a lower utilization rate than a server, its operational energy will decrease. Servers consume a massive amount of energy, but something like your smartphone doesn't use nearly as much. So for devices with a lower operational performance, the percentage made up of manufacturing energy becomes much, much higher. You should understand that the assumptions made here make the estimate for manufacturing energy appear smaller than it actually is. Globally, chip manufacturing consumes 100 terawatt hours per year. They say that 70% of that is in East Asia, and TSMC accounts for a fifth of that. Japan's total annual energy consumption is 1,000 terawatt hours per year. So that's 10 to the 14th compared to Japan's 10 to the 15th. When you consider that, you can see that a massive amount of energy is being funneled into chip manufacturing. This information comes from Google, so it's hard to say how impartial it is. But I'd say, since it's Google, that it's probably reasonably reliable, and the data itself is quite fascinating. This is the report for 2023. They announce environmental reports like this, and release them every year to show just how environmentally friendly they're being. I've kept the 2023 report in English, but to explain it in Japanese. From 2021 to 2022, their energy consumption increased quite a lot, by 18%. Here, they say they've managed to limit this increase to only 18% thanks to technical improvements, even as global demand rises much faster. Within that, they also mention that they've increased their percentage of carbon-free energy by this much, up to 64%. The pie chart they use is also quite interesting. The further down you go, the less carbon-free it is, while the green at the top represents carbon-free energy. This chart represents a 24-hour clock. This pie chart shows that the energy isn't carbon-free in the middle of the night, but is carbon-free during the day. Countries like Japan aren't carbon-free at all, but then you have the US, or places around here, where it's a bit carbon-free during the day. Because of solar power and other sources, we're seeing regions where the ratio of carbon-free energy increases during the day. Although nuclear power is also classified as carbon-free. So carbon-free doesn't necessarily mean solar, so that's what they're saying. Another report came out the following year, which stated that their electricity load increased by 17% in that 1 year. But that they've still maintained 64% carbon-free energy. That's what Google is saying in their report. As for how much energy generative AI consumes, there's a lot of different data available. It really depends on the task you give it, but first on the left, we have that IEA report again, and on the right is a paper published by the journal Nature, written by an entirely different group. I've brought both to show that even though they're from different sources, the data aligns reasonably well. The takeaway is that, as expected, inference consumes a considerable amount of energy. Here they're talking about energy of inference. But in the IEA report on the left, they're looking at text generation, and naturally the energy consumption is different depending on low or high. The vertical axis is energy consumption in watt-hours, and generating static images takes this much. When you go to the right, the scale of the axis changes completely, because it's video generation. But since you might not realize just how much 100 watt-hours is, the report provides comparisons, like your mobile phone's battery capacity, or the capacity of a laptop battery. For video, it depends on how much you're generating, but there's an assumption here. 8 frames for 6 seconds, which doesn't seem very long at all, but the report says this consumes enough power to drain your smartphone battery almost instantly. This is from the IEA report. And on the right is Nature, written by an entirely different set of authors. The diagram might be a bit difficult to decipher, but it covers things like image generation and text generation. On the horizontal axis here is battery capacity, and you can see from this that inference consumes considerably more energy than that. So while you all may be generating all sorts of things quite casually, you can see from this data that it's consuming quite a lot of energy. And finally, a few points to conclude. I know that you aren't necessarily only interested in low-power design. So I want you to consider these points when it comes to AI's interaction with society. This is about how to make generative AI green. CO2 emissions occur during AI training. The chart from earlier showed the consumption from inference, and there's CO2 emitted when manufacturing hardware. While training and inference are the predominant causes of it, it's actually not very clear which one is a greater cause. This is because, while a single training session requires much more computation, inference is performed much more frequently than training, and there's no way for anyone to know exactly how much inference is being done globally. But when you think about how many times each of you does it a day, it's quite a lot. So to make generative AI green, naturally this means we have to consider both training and inference. The first point doesn't impact training specifically, but it's to reduce the computational cost of AI models by using more efficient algorithms, architectures, and hardware. This is a topic that those of us in computing should really be thinking about. The second point is to adapt pre-trained models to new tasks or fields, rather than collecting new data or training models from scratch. This is what we call fine-tuning. I don't think many of you, when you're handling data in various fields and want to perform analysis using AI, will be building a training model from scratch. This depends on the field, of course, but it uses much less energy to slightly modify an existing model than to make one from scratch. This is extremely important as you move forward with your research. But of course, if the pre-trained model isn't very good, accuracy will suffer. While this will depend greatly on your specific application, it's something you'll need to consider. Finally, we should limit the use of large-scale models to cases where they provide significant value. While research may be an important application, it may be better to use a cheaper model. Or perhaps stick to free versions of generative AI when you're making static images or videos as a hobby. Of course, it depends on the value of the output, but I think how we use these tools will become a major issue for society as a whole. The fourth point is using generative AI to promote energy transition. For example, with solar power and other natural energy sources out in the world, power generation fluctuates constantly based on the weather. While where we're able to generate renewable energy may depend on the weather, we can save and distribute it, and deciding when and where to generate AI content based on the demand in society can help drive the energy transition forward. This might sound more like a discussion on power supply, but it's something we need to consider. We really have to look at this from a lot of different angles. Regarding that first point, I want to emphasize what is important from my perspective. From a computing perspective, so I've prepared this next slide. This is about the energy consumption of generative AI. It's from a paper published about 4 years ago. They ran the GPT-3 model on NVIDIA's V100 GPUs. As for TPUs, I'm not sure what you all think of Google, but they're actually currently making chips designed specifically for generative AI. TPU stands for Tensor Processing Unit. They've released a lot of different versions, but here they're at version 4. What Google is saying is that, and the green represents their chip, while red represents NVIDIA. I have my thoughts on the color coding here as well, but the model's parameters are massive, which is why the accuracy is so high. However, I'm not sure if you're all aware of the finer details, but you don't actually have to use the entire model. You can create what's called a sparse structure. By omitting the parts that don't actually need to be processed, you can significantly reduce the total workload. So what does that mean in practice? Something that would have taken 400 years on a GPU would only take 140 years on a TPU. That's for a single unit. If you have 144 units, you can do it in a single year. The point is that you can drastically reduce both the time and energy consumption. They're saying that this is what's possible when you build the proper models paired with the proper hardware. That was for version 4. But now in this later report, they've come to version 7. The vertical axis shows that they've managed to boost power efficiency dramatically, and they're emphasizing that this kind of technological progress is incredibly important. I have the technical reasoning for this here, but I'll skip it since we're short on time. Now let's look at these recent news articles. Regarding the importance of energy, that Nikkei Shimbun article from last April, and more recent ones have been asking, is there enough power to run AI? Or they'll report, Meta has signed a contract with a nuclear plant. Another crucial factor is transmission lines. It's not enough to have electricity, you have to supply it to the data centers. If you can't access the transmission lines, you could be stuck waiting 7 years. So power transmission is clearly a major hurdle. For example, in areas like Yokohama, they're generating wind power right in Yokohama port. Or even building data centers directly inside the power plants. When you think about it, which is easier, sending information or sending power? Right now, sending information is far easier. It's a little bit like local production for local consumption. But it's processing data right where the power is generated, and simply sending the processed information where it needs to go. So that's a technological trend that's emerged. Not really as a final summary, but speaking from a computing perspective, I've talked today about how to make computing green. Computing equals AI equals DX after all. I'm sure you all use AI in your usual research and in your daily lives in society. But it's not just about the GX of computing and AI in a narrow sense. You're all students under GX, so I want you to think broadly about how computing, AI, and digital transformation can best be used for the sake of GX itself. And with that, I'll bring this lecture to a close.